Welcome to a recorded presentation about breakaway couplings with Sean Anderson of Dixon Valve. And before we go any farther, Sean, could you just give us a little bit of your personal background?
Well, I was a college student about 20 years ago, and Dixon Valve was the local company, so I wandered over here and started working in the machine shop, and then I've had the opportunity to move through production control and work with special parts, move to purchasing, and I've worked with sales and some of our acquisitions over the years. I've been with Dixon 20 years, and now I currently am a product manager for specialty products, including dry disconnects and breakaways and some of those type couplings and parts.
Yeah, well, your machine background is probably helpful from the standpoint. We just did an interview with a gentleman who had analyzed a premature failure of one of the couplings on a marine application, and he emphasized the machining of the parts was one of the big variables, and that's why some of these things fail. The parts that are breaking, are supposed to break, didn't break when they were supposed to. Broke prematurely because of the machining aspects of it. So, certainly emphasize the necessities and skills there. But what geographic area are you covering for Mantek?
Our relationship for Mantek is we do sell their product worldwide, but we are pretty much the exclusive for North America, in particular the United States. So we're kind of the exclusive channel for providing those products. We work very closely with their sales and engineering teams, and we in fact influence some of the product designs and work on product designs and making them more suitable for specific applications that we get involved in here. We really take a hands-on approach to working with engineering and application problems and difficulties, and fine-tuning our products to meet the service that they're in.
Okay, well, I think that gives us a nice background, and we're ready now to proceed. So why don't we hear about both the industrial and the marine couplings, and I may interrupt you with a question or two, or I'll certainly have some at the end. So fire away.
Okay. Dixon Valve has been around for about 95 years. We started in the industrial sector with hose and couplings, and have continually expanded to more and more engineering parts. Today, what we would like to do is talk about three specific types of breakaways. And on the next slide from this one here is the three different types. The industrial version, the marine version, and we'll just briefly touch on a non-closure version for this. So starting with the industrial, many people get it confused in that this is limited to only industrial applications. It is the most suited for industrial applications, but we have seen several marine applications for this particular breakaway style as well. Basically, it utilizes 3 bolts that are engineered and designed to yield or break at a certain amount of force applied to them. The industrial version is designed in such a manner that it can be activated when stresses or forces are applied up to a 90-degree angle to it. Many different types of breakaways, such as cable and in particular the marine ones, need to have axial tension in line to pull the bolts, where the industrial can act as kind of a shear or a side motion to it. These are particularly used when attached on one side to a fixed point, such as a pump or a manifold or a piping system, and then the hose comes out of the other end, so that one side is fixed and the other side connected to the hose would be connected to the vehicle or whatever would move. So if we could go to the next slide. Okay. These minimize the amount of spillage by activating poppets that are spring-loaded inside. So it provides protection against a situation where a hose, manifold, or something is going to be subjected to a high degree of force. And what we try to do is work with the particular application with the weights and forces that are going to be involved and the angles to custom set the bolts when needed for specific applications. In doing that, we can eliminate overloading the stresses on pipes so that pipes don't break free and pumps don't come off their mountings, and the manifolds, no damage is done to those, as well as protecting the hose. What we want to do is go about 25% more than what we expect the stress to be in a normal application. Therefore, we don't put excessive load on the hose and tear the hose apart. So it's a pretty simple system. It automatically senses that excessive load by the fact that we're pulling on these bolts. When the bolts give way, the poppets close, it disconnects, and things can go free. It operates independently of other safety systems. It's just kind of, you put it in service and it's there. And because it's a pretty simple in that it is a braking bolt that will, we know it's going to yield at a certain point, it doesn't require any other monitoring or cable or power sources or anything else. It sits there until we have too much force, and then it pops and seals off and can be easily repaired. We do it in many different variations, and we have slides further on, and we'll show some of the different combinations of threads and different types of seals. The slide says they're available in 1, 2, 3, 4, and 6. We are continuing to fill out the line. We can offer 5, 8, 10, and 12-inch breakaways currently. The material for the marine ones in marine applications would generally just be stainless steel. This is a kind of a breakdown or kind of a slice of it, so we could look at a couple of the parts. In the slide, we're pointing out the stainless steel braking bolts, and if you look very closely in the center, you'll see there's kind of a neck down portion. That's the engineered part of this whole thing, where we machine that groove down so that it will yield at a given point. And we talk about that in terms of KNs or kilonewtons, in terms of energy needed to break it. Point out a rubber bumper that's on the outside. That's just when they separate, rather than the metal bouncing across the ground. We've got a rubber bumper. All the internal components would all be stainless steel, including stainless steel pins and poppets, and all of that kind of interior hardware is all going to be stainless steel. We point out the Viton O-rings. There are 3 wetted seals, one on each one of the poppets that closes independently when they separate, and there's one where the 2 halves join together. And so as far as repair kits, it's fairly simple. You're going to probably have, in most cases, 3 seals that are going to be wetted seals. We occasionally have some other types of variations that have dust seals on the outside that are protective, but pretty simple and pretty straightforward as far as how the parts go together. In this slide, what we're trying to do is just to give you a little bit better idea of an application of an industrial one. And, industrial breakaways are typically installed on the loading arm manifold piping system, one side being rigid, the other side being connected to the hose. And when it's broken away, you can see the other slide. This would be maybe somebody driving away, or maybe ship pulling away or something. And the bolts snap, and in that case, the poppets snap shut, and the only real loss is the bolts, which are a replaceable item. There's a kit for the bolts. Again, I was talking about the different sizes. This is kind of an indication of the size and what our standard KN or kilonewton rating is on it. We can customize this for different purposes, but there's 3 bolts, and so in the case of what we call axial tension or in line with a hose and pipe, all 3 bolts are going to take up that force, hopefully evenly, as it pulls in line. So your KN force for, say, let's say a 4-inch part is listed here as 52 KN, 52,000 newtons or kilonewtons. Excuse me. And when you pull in force, all 3 are going to hold at that given level. If you had a side motion on the industrial, which allow that side motion, one of the 3 bolts typically is going to see the excessive load first, and so you would divide the amount in thirds. In the 3-inch, we got 33, so each bolt individually will hold 11 KNs. And again, that's specific to this type of coupling that's industrial. I think the next slide will be the marine version, and we'll talk about that. The marine version is installed usually between 2 lengths of hose. So it incorporates the same internal mechanisms and is very hard to tell from the outside the difference. The difference in the engineering basically is that we isolate those bolts so that they can't see non-axial tension. They can't see a force that's on a side load. In a marine version where these are applicable, you could think about 2 lengths of hoses going over the side of a ship and going down to a work boat or to another boat, and there's going to be pitching and rolling and drifting and some of those things going on because of the sea and the waves and everything. We don't want this to react to that side sea motion, heaving and hauling of the boat. What we want it to do is only react if the boat starts to drift away and we take up tension on the hose string, and therefore it will all 3 bolts will then shear, break off, and allow the 2 parts to separate. When the hose tension gets too great, the boats are drifting away and there's nothing stopping them, these will break before we get to the point where we do any damage to any of the couplings or the hoses or anything like that. So it has increased resistance to torsional bending forces. Going on to the next slide, again, we're pointing out applications, ship-to-shore or offshore platforms, ship-to-ship transfer. Again, we want to emphasize that the marine version is specifically designed to be in a hose string. In many applications, you'll have say a 25-foot and a 75-foot length of hose going over the side of an offshore oil rig, and this will be a mud or fuel hose, and in between those 2 lengths of hose would be where this marine breakaway would be applied. It senses that excessive load. When the bolts break, pulls apart, the pop is shut, disconnects, and seals off. The release is executed quickly, and so there's a very minimal amount of loss of product, and the bolts are pretty dependable. They've been around for a long time, so the engineering's been worked out pretty well, and they're a pretty reliable, dependable system. And again, because we're using bolts, there's no cables to worry about getting twisted. There's no electrical system that needs to be monitored or sensors or anything like that. We just, when we exceed the rate, it snaps and shuts off. Again, we do offer a different material, but stainless steel is pretty much what's going to be needed for actual marine service. Breakaway or cutaway of the breakaway here. Again, if you looked at it, you're going to see it's pretty much like the other one. The only difference I'll point out here is if you look between the blue bumpers and below where we're pointing for the stainless steel bolts, if you were to compare that to the other side, you would see that this area here this overlap is longer, and in fact, it covers the area where the breaking bolt is. So therefore, when there's side load to it, this extended flange area is going to hold the parts so that it's not going to, the bolts are not going to see that stress. They're only going to see that inline axial tension to it. Again, we have the bumpers on the outside. All internal components are going to be stainless steel. Everything's 316 stainless inside here, with the exception of the spring, which is PH7, which is a regular stainless steel spring. And we'll go over some of the other types, and we'll mention the O-rings a little later. Here we see the marine breakaway applied between two hoses, emphasizing that this is in a hose string. And we're showing in the other picture the bolt snapped and everything being lined up straight, because we need to hold on all three of those bolts to eliminate wave reaction and it breaking prematurely. Again, we're kind of going over that same part again. It minimizes the flange minimizes that side load that's applied to it, so we're in line, and the braking force is the same for both the industrial and marine. But of course, when we're talking here in a 3-inch, a 33, a 4-inch, or 52 kN, we're going to see all that load applied because we're preventing it from breaking to the side. So it will need that full amount of force, and the hose will have to be engineered sufficiently to withstand that force. Again, we can customize those bolt settings by machining them down by review. Most of the marine hoses and dock hoses are very heavily built. They're very severe. So these forces fall well in line with the expected braking loads, or well below the amount of any damage done to hoses. Little diagram here shows you kind of what's going on inside. There's two sides. Each of them have a spring-loaded poppet on it, similar to some of the dry disconnects that we make. When the force exceeds the amount the bolts can handle, they snap, the valves separate. When the valve separates, the pins that were pushed, that were holding the springs open, they're released, and the spring shuts this, or the spring drives the poppet, as well as the weight and internal pressures. So if you have weight, like on, say, a mud transfer hose or a long string of diesel hose, and an internal pressure, that's just going to add to, basically the speed at which this thing is going to seal. And because there's a taper on the poppet, it's called blowout proof. So even when you have that dead-headed pressure, these poppets can eject. So it's a very, very safe and very dependable, very secure seal. Here is kind of just kind of gives you some of the different variations we can do, male and female, NPT and BSP threads. We can do Victalic thread or Victalic fittings. We can do flanges. There are some special DIN flanges that we do, as well as 150-pound, which is fairly common, and 300-pound flanges. And also, like the bottom right hand is one that's becoming popular in some of the industrial versions, where you have a piping system and perhaps a valve or something, and you can bring a 150-pound flange up to the one side on your pipe, and then on the other side, a lot of hoses are made with a male NPT thread, so female thread just threads into it. So we can do these different variations with one side one way and the other side another way. Helps you bridge the gap. Just a flow diagram. I don't want to get into that too much, but they have what's generally considered pretty good flow for their size, and typically matches up to standard flows you're going to see in hose transfer and pump operations. Kind of a list of some medias, fuel, seawater, wastewater, just all kinds of different things that this can actually be applied to. One of the things I wanted to kind of mention here is an application versus the marine and industrial. If we were to think of a situation like a lightering, where you have a large tanker can't come into a port, so a lightering tanker is sent out to offload some of it to come into a more shallow port. What happens is the two tankers run parallel to each other at a given speed and course. Hoses are sent between the two different tankers, and the offloading process, would begin. This particular application could use either industrial or marine, depending on how the hose setup is done and how they want to have it engineered. On the manifold on either side of the main tanker or the lightering tanker, you could have an industrial that breakaway that's bolted directly to the intake manifold on the piping system on the individual tanker. Then the hoses would slump off, go down and up to the other tanker. If the lightering tanker changed direction or lost power or course came off or whatever happened, you could imagine these tankers starting to drift apart. And let's just say one lost power suddenly and the other one didn't realize. You'd have that kind of side movement where that industrial version would see the one pulling ahead of the other and snap and break away and allow the two tankers to separate before they had to, you had to get guys in there to disconnect everything with the hose tension going on. Likewise, a marine breakaway could be used here as well. If there were two lengths of hoses joining, then the hose would go from, say, the main tanker down, it would go into a marine breakaway, and then the hose would extend up to the lightering tanker. As the tankers started to drift apart, because the hoses are gonna kind of adjust themselves on the angle, we can still see that axial tension on there, but as they're heaving back and forth, it's not going to respond, being in the middle of the two different hoses with the two ships bouncing apart from each other. So that's kind of just a little visual there to tell you different ways in which you could use these breakaways, even though one's called industrial and marine. We go to the next slide. Very briefly, we also make them with a non-closure, and a lot of people were wondering, well, why would you do this with a non-closure system? One of the applications on the industrial side we've seen is they add a water intake, and trucks will drive off while still connected to the hoses. And in sanitary, all the piping is obviously stainless steel. So if a truck drives off and rips the piping out, it's thousands of dollars that is lost in piping, as well as a bay down for however many days it'll take you to get the bay repaired and that opening put back up. So there can be potentially a lot of lost time. Even though the product is only water, there's a lot of money that can be lost to the damage due to having a facility out of service. So in this case, this breakaway just breaks the water contents inside spill, but it breaks before we do any damage to any of the hoses or the metal piping in particular. A little picture here. This is actually in South Africa, where this is a loading system for loading trucks with fuel, and there's a breakaway applied before the API. In a couple cases, they were driving off, and you had a 4-inch line with gasoline or diesel spilling out, and that could be a potentially pretty hazardous situation. So breakaways were put in place here to prevent that. And then that's the last slide. So hopefully this information is useful.
Very useful. That's a very good presentation, and some of those slides helped me understand the mechanics a little bit better than I did before, so I appreciate that as well. You mentioned that you've expanded into the 12-inch. Are a lot of the marine applications in those larger sizes?
The marine applications we're seeing right now are fairly specific at this current time in actually 2, 3, and 4, and these breakaways are basically standard fare for offshore oil platforms in the Gulf. Okay. And so you're seeing diesel and mud transfer hoses in 2 and 3, and sometimes potable water that's going in a 2-inch. And again, they don't want to do any damage to any of the hoses, so they just specify a breakaway in there.
That makes sense.
We are seeing some 8-inch on dock transfer hoses for large scale offloading and loading of barges and like oil tankers. Okay. And then 10 and 12-inch are some of those lightering things that we're talking about there. Those sizes get pretty big because they're doing 5,000 barrels per hour transfer rates.
Sure. So those would have to be quite large. We did an interview with Berkeley Engineering, and they had analyzed a premature failure of a Gall-Thompson breakaway coupling, and they concluded that it was very difficult. Back to your experience with the machining again, that it all came down to machining that breakaway bolt there, and that in this case it broke with far less than the anticipated force, and did so prematurely. And they so number one, commenting on how you assure the reliability of the product.
We use very careful inspections on the metal that we're using to cut these bolts. They're not like you buy a bolt and then machine a groove into them. We take raw material that is highly specified and heat traceable certs and those type of things, and then we machine a specific groove, knowing that the yield point of this specific metal is at a given rate. The trick that comes into this is that when you're doing this, you really don't know the loads and how they're going to mount up. You can theorize how they're going to go, but in applications and you get different types of angles, then you start to have a lot of other things that overlap, and that makes it not quite as straightforward as I tried to make it for here. That's where there's a little bit of trick in the specification of the bolts, and trying to make sure you have more than enough to cover kind of field handling and rough service that you don't expect in a laboratory when it's sitting on the bench.
And another comment that he made, I'd like to have you talk about that, is he was not sure you needed the breakaway coupling. He talked about quick release couplings, and I'd assume what he was talking about there was something that the operator himself has to release it rather than, it's released by the forces. Would you want to comment on why you need something that automatically breaks rather than having an operator quick releasing it?
Well,
I guess you probably answered it just by talking about things like gasoline trucks driving away with and so forth, but go ahead.
Yeah, I mean, I don't really know what he's commenting on, so I'm making a general comment which may not directly reflect the application that he was talking about. But in the instances that we're familiar with here, where you have say mud hoses and diesel fuel hoses, the hoses are lowered off the deck of an offshore oil platform down onto a workboat, and they have dry disconnects that we make that are on there, which seal the hoses up and are relatively easy to do. You line the coupler up and you just twist it, and that mechanically locks it and opens everything up. Likewise, if you had to disconnect, you kind of grab the handle, rotate it back, and pull it off. It is fairly simple, but in the instance where, let's say, you have drift, it gets a little bit dangerous to send somebody in there when there starts to be tension onto the hose. And now you have the hose, and depending on the drift and all, if we start to pull on that, the operator is fighting all that load that's on the rollers and the mechanisms inside, and he's there next to a hose that could potentially have tension in it.
Yeah.
And if he disconnects it, he could get knocked right off the deck.
Oh, yeah. Yeah, there's a lot of safety aspects here.
So this breakaway would prevent that. They can let it go to the shear point of the groove, and then they don't have to have the operator near those tensioned lines. In the tugboats and those kind of stuff, they watch out for that, because that's pretty dangerous when you have a line under high tension.
What's the typical life of a marine breakaway coupling?
If you were to put it in service and everything was pristine and was well maintained and everything, I would anticipate, as long as 5 or even 10 years. But as we all know, these things get bounced on the deck, and they're not gingerly handled, nor do they see pristine environments where there's not elements of salt and other chemicals attacking it. So what we suggest is a visual inspection before use, just to look at it and visually see. You can kind of look to see how the coupling's doing as far as abuse, and we recommend a yearly inspection just to take it apart, look at the bolts, perhaps service the O-rings. They're pretty inexpensive, and if you maintain that, then the outside of the body has a good amount of stainless steel in it to resist wear. So again, like a mud service sees an abrasive on the inside, and that's going to wear it down, where water or diesel fuel would not wear it, but over time it'll get weaker.
Sure. One last question. We're heavily involved in the power plants, and so we're interested. You mentioned power plant construction as opposed to the typical, I guess, fuel loading, unloading. What would you have during the construction phase that would be different than normal operation in the power plant?
During construction of a power plant or construction of the unit, the breakaway?
You'd listed power plant construction as
Oh.
opposed to just power plant, so I was just curious as to what that application was.
Well, we've actually worked with a power plant in the Midwest that I'm not sure their exact circumstances, but it would appear that they needed to receive, I would guess it's excess cooling water maybe that's particularly treated for the boilers. And they had an application where a truck driver was driving away, and I guess the hose was not disconnected, and it was danger. I don't know if the guy got pinned or something like that, but it was a pretty dangerous situation. They're looking at a breakaway in this application, so that in case that again happens and somebody accidentally drives off while this, in this case it was a water hose, was connected, it would break and the operator would not be trapped behind the hose in the truck and a wall. So applications like that we've seen for not particularly necessarily power plants, but for some other type of heat transfer units where they're using some hot water and they need to disconnect reactors or steam lines. We've seen a couple applications like that.
I see.
Also, I know that the different types of we visited a nuclear power plant in California, and they have some hazardous chemicals that they have to deal with for treatments of water, I guess, and other types of they've got some caustics and some acids, and again they were looking at the potential of in this case a 2-inch line, but a drive off with a line that's 2-inch flow of a heavy caustic or acid is certainly at least a large environmental remediation problem.
Yeah, sure. It certainly would be. Yeah, and they're using, of course, sulfuric acid and hydrochloric acid and other things like that. Yeah. Well, Sean, it's been very interesting. Very good presentation. I'd like to thank you, and I'm sure we'll be touching base with you again. But thanks very much for the interview.
All right. Thank you. I appreciate it.
Right, bye now.
All right. Bye.